This video looks at equilibrium. By the end of this video, you should understand what it means for a system to be at equilibrium.
Prior to now, we've only been looking at reactions that go in the forward direction. In other words, reactions that go until the reactant runs out. However, this isn't always the case. Many reactions are reversible reactions. These are reactions in which the products can regenerate the original reactants. For example, given this reaction here, 2 moles of NO2 yielding 1 mole of N2O4, this reaction is reversible, meaning it can also run in the opposite direction. 1 mole of N2O4 can break down to form 2 moles of NO2. Equilibrium refers to the state of a system when there is an exact balancing of two processes which are opposite of each other. In other words, the rate of the forward process is equal to the rate of the reverse process. Because the rates of these opposite processes are equal, there will be no net change to the system, even though both processes are still occurring. Consider the population of New York, for example. If the rate of people moving out is equal to the rate of people moving in, we'll always have a constant population. However, both the moving out and moving in processes will still be going on, but their rates are equal, so there's no net change to the population. To take another local example, here we have Staten Island and here we have Brooklyn. As you probably know, the Verrazano Bridge connects Staten Island and Brooklyn. Imagine that one morning there are 24 cars in Staten Island and 37 cars in Brooklyn. If the rate of people driving over the bridge from Staten Island to Brooklyn is equal to the rate of people driving over the bridge from Brooklyn to Staten Island, we will be at equilibrium. We'll always have the same number of people or the same number of cars in Staten Island and in Brooklyn, but they won't be the same cars because cars will be going consistently over the bridge. The rate of people going from Staten Island to Brooklyn is equal to the rate of people going from Brooklyn to Staten Island. Chemical equilibrium is the state of a system where all the concentrations of the reactants and the products are constant, and the rate at which they form is equal to the rate at which they are consumed. So again, we have constant concentrations and equal rates. This is a dynamic system. It's not static. In other words, both the forward and the reverse process are still happening. We just don't see any overall net change. It's important to note that the equal in equilibrium refers to the rate, but not necessarily the amount. It doesn't matter if the amounts of reactants and products are equal. They might be, but that would just be coincidental. What's important is that the rates are equal. Any reaction in a closed container will eventually establish equilibrium. And equilibrium can occur for both physical and chemical processes. Take this example of a physical equilibrium system that we've seen before. The first picture shows a liquid placed in a closed flask. As soon as the flask is closed, some of the liquid will begin to evaporate. After a while, there'll be a goodish amount of particles in the vapor phase. This means that some of the vapor particles can begin to recondense. Eventually, the rate at which particles are evaporating will become equal to the rate at which particles are recondensing, meaning that we'll be at equilibrium. Once this point is reached, the liquid level will remain constant because the rate of evaporation is equal to the rate of condensation. Looking now at a chemical example, we see when we first put N2O4 gas in a container, it will begin to break down to form some NO2 gas. Notice this equation is not balanced. After a while, some of this NO2 gas will start to react to again form N2O4. When the rate of the forward reaction, N2O4 to NO2, is equal to the rate of the reverse reaction, NO2 to N2O4, we'll be at equilibrium. Here, a sign that we're at equilibrium will be the constant color of the container. Since NO2 is a brown gas, since we'll have a constant amount of NO2 at equilibrium, we'll have a constant brown color. In terms of notation, we use a double arrow to indicate that a reaction occurs in both directions, or that a reaction is at equilibrium. The proper way to draw this arrow is like this, but since that's a difficult symbol to type, I just usually use this double-headed arrow. But when you're drawing it in your notebook, you should draw it like this. Let's take another look at an example. This reaction tells us that 1 mole of H2O plus 1 mole of CO will yield 1 mole of H2 and 1 mole of CO2. That's the forward reaction. But notice, because of the arrow, we see that this reaction establishes equilibrium, because eventually the rate of the forward reaction will equal the rate of the reverse reaction. Take a look at this particle diagram. Notice the amounts of each particle are listed in the table below. Pause the video here and try to decide where the reaction reaches equilibrium. If you said these two flasks, you're correct. Notice that at that point, the amount of reactant and product is constant, meaning the rate at which reactants are forming products is equal to the rate at which products are breaking down to form reactants. Looking at this same information graphically, here we see a graph of reaction rate of the forward and the reverse reaction. The rate of the forward reaction is represented in blue, and the rate of the reverse reaction is represented in pink. Notice that initially, the rate of the forward reaction is very high, and the rate of the reverse reaction is very low. This makes sense since there can't be any reverse reaction until a good amount of forward reaction has occurred. Eventually, however, the rate of the forward reaction will begin to slow down as more reactant is converted to product, and the rate of the reverse reaction will begin to pick up since there'll be more product to reconvert to reactant. Eventually, these two rates will converge and will be at equilibrium. Looking now at a graph of concentration of reactants and products, we see that in each case here, we begin with a high concentration of reactant and a low concentration of product. This is reasonable since at the start of the reaction, there's no product yet formed. But as the reaction proceeds, the concentration of reactant will decrease and product will increase until they become constant when we reach equilibrium, the point at which the rate of formation of products is equal to the rate of breakdown of products back into reactant.
That brings us to the end of this video. Let's review our goals. In this video, we looked at what is meant for a system to be at equilibrium, meaning the rates of the forward and the reverse reactions are equal and the concentrations of reactants and products are constant.